A comet from another solar system, 3I/Atlas, should trail its past, but the newest images reveal a tail pointed directly toward the Sun. Is this bizarre anti-tail just a cosmic trick of perspective, or a sign the object is actively braking, maybe even under intelligent control? Right now, it's hiding behind the Sun, crucial images locked away in agency vaults. With more mass than any interstellar visitor before, what we can't see may upend everything we know about cometary science and possibly about our place in the cosmos. So why does 3I/Atlas refuse to play by the rules? And what are officials not telling us as the clock ticks down to its return? In the world of comets, tails usually tell a simple story. Dust and gas stream away from the Sun, pushed back by solar radiation and the solar wind. But 3I/Atlas defies this pattern. Its forward-facing anti-tail, caught in recent images, challenges the classic rules of cometary behavior. To understand how such a feature can appear, it helps to look at the dance between dust, sunlight, and the observer's point of view. When a comet nears the Sun, sunlight heats its surface, causing ice to vaporize and eject dust grains into space. Radiation pressure from the Sun acts like a giant invisible broom, sweeping the smallest grains into a long tail that always points away from the Sun. Yet, not all dust reacts the same way. Larger grains, often hundreds of microns across, are heavier and move more slowly. Instead of being swept back, they can linger close to the comet's orbital path, forming thick, subtle trails. When Earth lines up at just the right angle, these dust trails can look like they stretch ahead of the comet, creating an anti-tail that appears to point sunward, even though the grains themselves are simply lagging behind in the comet's orbit. This geometric illusion has been seen before, most notably with 2I/Borisov and a handful of solar system comets. The effect depends on the interplay between the Sun, the comet, and the observer's location. As the viewing angle shifts, so does the apparent direction of the anti-tail. For 3I/Atlas, the anti-tail's brightness and sharpness have drawn attention. Some astronomers argue that the feature is too pronounced to be explained by geometry alone. They point to the possibility of active processes, like jets or even controlled propulsion, pushing material forward in direct opposition to the Sun's pressure. If true, this would require energy input far beyond what's typical for natural comets. Models show that a truly engineered anti-tail would likely have a uniform grain size, a sharply defined edge, and possibly even signs of periodic release or sudden changes in direction. In contrast, naturally produced anti-tails tend to be made of a spread of grain sizes, with their shape and brightness changing as the comet rotates or as the viewing geometry shifts. For 3I/Atlas, the jury is still out. Radiation pressure, dust production, and the unique alignment of Earth, Sun, and comet all play a role. But so far, no unambiguous evidence points to artificial thrust. The only other interstellar visitors, Oumuamua and 2I/Borisov, each sparked their own controversies. Oumuamua showed no tail at all, but did accelerate unexpectedly. Borisov, on the other hand, looked and behaved much like a typical comet, though it too displayed a faint anti-tail at certain angles. 3I/Atlas, with a mass up to 1,000,000 times greater than Oumuamua, brings new weight, literally and figuratively, to the debate. Whether its anti-tail is a trick of perspective or a sign of something more, the coming observation windows will be critical for settling the question. Behind the Sun 3I/Atlas moves unseen. For weeks, ground-based telescopes have gone blind, unable to track the object as it slips through the glare. The critical perihelion window, when the comet is closest to the Sun and when any sign of non-gravitational movement might be clearest, has arrived with almost no fresh public data. Pre-conjunction images, captured just before the Sun swallowed the comet from view, remain locked on agency servers. The official explanation is procedural. A government shutdown in early October stalled routine data releases and delayed the review process for sensitive frames. This blackout is more than an inconvenience. Without access to the most recent images, astronomers can't refine their models or confirm the nature of the anti-tail. Rumors fill the vacuum. Online forums and social channels overflow with speculation, Some claim evidence of propulsion, others insist the anti-tail is already proven artificial. In reality, the only thing confirmed is the absence of new data. Requests for early release have been met with silence or boilerplate statements about operational priorities. Even international partners, who sometimes offer parallel streams of information, have reported delays in sharing their own observations. The timing could hardly be worse. The period just before and after perihelion is when subtle changes in motion, brightness, or tail structure would be most apparent. Instruments on Mars orbiters and deep space probes are still collecting data, but their results are subject to the same bottlenecks. As of late October, the last available public frames date back nearly 3 weeks. For a fast-moving interstellar object, that means models of its trajectory and outgassing are already drifting out of date. The sense of urgency is palpable across the astronomical community. Some teams have resorted to tracking the object with smaller, less sensitive instruments, hoping for a lucky break in the sun's glare. Others are combing through archival images, searching for overlooked clues. The wait for new data is more than a scientific frustration. It's a race against time, with the possibility that key evidence about 3IATLASs' true nature could slip by, unrecorded, while the world is left in the dark. Avi Loeb, chair of Harvard's astronomy department and founder of the Galileo project, has become one of the most talked about figures in the debate over 3I/Atlas. Known for his willingness to challenge orthodoxy, Loeb's reputation was cemented after he argued that Oumuamua, the first known interstellar object, could be artificial. Now, with 3I/Atlas, he's published 2 papers examining the anti-tail's possible origins, both natural and technological. Loeb's approach is rooted in what he calls the technosignature framework. Treat every anomaly as a potential clue, and test natural explanations as rigorously as possible before ruling out artificiality. For Loeb, the question starts with the basics. Is there even dust in the anti-tail? Without dust, the geometric illusion vanishes, and the only explanations left would be active processes, jets, outbursts, or something engineered, but the available data is ambiguous. Some images hint at a dense, sunward plume. Others are too blurry or faint to confirm. Loeb's first paper models the anti-tail as a product of viewing geometry and large, slow-moving dust grains. His second paper pushes further, asking whether the sharpness and brightness of the anti-tail could be matched by any known comet or whether something more is needed. The mass of 3I/Atlas adds to the puzzle. By standard estimates, its nucleus is several kilometers across, with a mass as much as 1,000,000 times greater than Oumuamua and up to 1,000 times more than Borisov. This isn't just a statistical outlier, it's a leap in scale that, for Loeb, demands close scrutiny. If the anti-tail is being shaped by outgassing, the sheer size of the object means that even small non-gravitational forces, like those from jets or hypothetical engines, would be easier to detect than in any previous interstellar visitor. Loeb's Galileo project, which coordinates telescopes and data analysis worldwide, has taken a leading role in the hunt for technosignatures. But Loeb is quick to point out that the scientific process has to come first. Extraordinary claims require extraordinary evidence. Until the next batch of high-resolution images is released, the debate will hinge on what can and cannot be ruled out. For now, the anti-tail remains a test case for how science navigates the boundary between the known and the possible. On July 1, 2025, the Atlas telescope in Chile picked up a faint, fast-moving object on a hyperbolic trajectory, clear evidence of an interstellar visitor. Within hours, astronomers worldwide began scouring archives, uncovering images from mid-June that confirmed 3I/Atlas's path. The discovery triggered a global rush to schedule observations before the comet vanished behind the sun. Each team raced to secure a window, knowing the opportunity would not last. The urgency was unmistakable. With perihelion set for October 29th, the time to catch any sign of non-gravitational movement was slipping away. At 203 million kilometers from the Sun and traveling at 68 kilometers per second, 3I/Atlas would soon be lost in solar glare. Ground-based telescopes faced strict limitations, while space-based assets like Mars orbiters and Hubble competed for observation slots. Schedules mapped out months ahead were upended. Mars science targets were postponed so HiRISE could capture images at 30 kilometers per pixel, 3 times sharper than Hubble's best for this object. Unlike the formal alerts for hazardous asteroids, the International Asteroid Warning Network did not issue an official campaign. Instead, a patchwork response emerged. Observatory directors coordinated by email, mission planners consulted across agencies, and research teams posted open calls for data. The Galileo project shifted its network to track the object, while social media buzzed with the sense of a rare one-shot chance. The possibility of witnessing an interstellar object at perihelion, where even a small deviation could reveal active thrust or outgassing, was not lost on anyone. Pre-conjunction images were logged and analyzed for subtle changes in the comet's tail or motion. Teams at Mars and on Earth prepared for synchronized observations as soon as 3IATLAs reappeared. Each dataset promised to refine trajectory models and, if lucky, settle the debate over the anti-tail's origin. For some, it was a test of planetary defense. For others, a chance to study the physics of interstellar comets. And for a few, it was the hope of finding proof that our solar system is not alone. At perihelion on October 29, 2025, 3I/ATLAS races past the Sun at a distance of 1.36 astronomical units, about 203 million kilometers, and reaches a velocity of nearly 68 kilometers per second. This is the moment when any sign of unnatural movement, whether subtle or dramatic, would be most apparent. For astronomers, the perihelion window is not just a milestone on the calendar. It's the best shot at catching a physical signature of thrust or braking, evidence that could separate a natural comet from a technological object. The geometry is unusually favorable. With the comet's trajectory sweeping through the planetary plane, close to the orbits of Mars, Venus, and Jupiter, even the smallest deviation from its predicted path would stand out. If 3I/ATLAS were to accelerate forward, gaining energy, or slow down as if applying brakes, the resulting shift in its orbit would ripple through the ephemeris. Tracking instruments like HiRISE on Mars Reconnaissance Orbiter are tuned to detect changes as small as a few millimeters per second squared. That's a sensitivity fine enough to catch the kind of course correction a spacecraft might attempt. The possibility of a probe release adds another layer of anticipation. If the main body of 3I/ATLAS is simply a carrier, smaller objects could be ejected at perihelion to exploit the unique geometry. A probe, released in just the right direction, could use a slingshot effect from the Sun's gravity to change course in ways that a passive chunk of rock never could. Even if the nucleus itself doesn't deviate, a sudden appearance of a secondary object moving independently would be impossible to explain by normal cometry physics alone. The stakes are sharpened by the comet's mass. At up to 1 million times the heft of Oumuamua 3I/ATLAS is not easily nudged. Any measurable change in velocity or trajectory, especially at this scale, would demand an energy source far beyond solar heating or random outgassing. That's why every available instrument, from Mars orbiters to ground-based telescopes waiting for the Sun to move aside, is focused on this brief window. The data gathered here will define the limits of what's possible for natural comets and what might still be possible for something engineered. The world is watching for a verdict written not in speculation, but in the numbers. Tracking 3. I/ATLAS relies on a web of instruments, each shaped by its own technical boundaries. The Mars Reconnaissance Orbiter's HiRISE camera is at the center of this effort. At perihelion, HiRISE achieves a resolution of about 30 kilometers per pixel, 3 times sharper than Hubble for this target. That precision allows HiRISE to spot shifts in the comet's position or the sudden appearance of a secondary object if the geometry and timing cooperate. The Mars team has had to weigh priorities, sometimes delaying routine science to secure imaging slots for the comet. Competition for these windows is intense, and the threat of solar interference is constant. When 3I/ATLAS nears the Sun from Mars's perspective, scattered light and camera artifacts threaten to drown out the faint signal. teams adjust exposure times and image processing methods in real time, trying to pull meaningful data from the noise. Earth-based telescopes face their own hurdles. During perihelion, the comet is nearly hidden behind the Sun, making direct observation from the ground almost impossible. Only after 3I/ATLAS swings away from the Sun in November can ground observatories, like those in the Galileo project's global network, resume tracking. These telescopes, spread across continents, are ready to capture rapid-fire images and spectra as soon as the object re-emerges. While the Galileo project can't match HiRISE's pixel resolution, its flexibility and global reach fill the gaps left by space-based sensors. Other Mars orbiters, including ESA's Mars Express and ExoMars Trace Gas Orbiter, add to the watch list. Their instruments monitor dust, gas, and outbursts, providing chemical context to the visual record. Each observation is logged with precise timing and geometry, building a detailed ledger for later analysis. Solar interference remains unpredictable. Even the best sensors struggle when the comet sits close to the Sun. Careful calibration and cross-checks across platforms are essential. As the Sun's glare fades, a flood of new data will challenge every assumption about interstellar visitors. December 19th stands out on every astronomer's calendar. That's when 3I/ATLAS makes its closest approach to Earth, offering the best chance for ground-based telescopes to capture high-resolution images and spectra. Observatories across the globe, from the Galileo project's network to major research facilities, are preparing for a surge of data. These images could reveal fine details in the anti-tail, subtle changes in the nucleus, or even unexpected outbursts. But the search for answers doesn't end with visible light. As the comet passes near Jupiter in early 2026, the Juno spacecraft will listen for radio emissions, signals that could hint at technological activity if anything unusual is detected. This multi-pronged approach, blending optical imaging with radio monitoring, is designed to catch both natural and artificial signatures. The next few weeks will be decisive, as every instrument lines up for what may be the final word on 3I/ATLAS's true nature. In a moment like this, patience is more valuable than speculation. Viral posts and dramatic headlines often race ahead of the evidence, especially when data is scarce or delayed. The scientific community relies on validated datasets, raw images, published ephemerides, and peer-reviewed analysis to draw conclusions about 3I/ATLAS's behavior. Claims of sudden course changes or artificial signals should be ignored until confirmed by official channels, such as mission archives or recognized observatories. Trusted sources, including the Galileo Project and Space Agency data portals, will release results as soon as they are independently verified. Until then, the best way to stay grounded is to wait for the numbers, not the noise. In this field, every major discovery is built on careful measurement, not rumor. 3I/ATLAS is only the third interstellar object ever observed, discovered by ATLAS on July 1, 2025. Its forward-facing anti-tail, visible in images before the Sun concealment blackout, challenges our understanding of comet behavior. Experts like Professor Avi Loeb have published peer-reviewed analyses weighing geometry-driven dust illusions against the possibility of artificial propulsion. The object's mass, estimated at up to 1 million times that of Oumuamua or Borisov, raises the stakes for every data point. As of now, pre-conjunction images remain unreleased, and Earth-based telescopes are limited by its position behind the Sun. The International Asteroid Warning Network has launched a coordinated observation campaign, with decisive windows set for October 29th and December 19th. Still, the presence of dust and the true cause of the anti-tail are unconfirmed. Until new images and validated datasets arrive, the nature of 3I/ATLAS remains uncertain. In the next weeks, science, not speculation, will decide if this is a comet like no other or evidence of something far stranger.